Days, Italy, 2017, 11th of May. There will be coding. There will be Abraham Lempel and Jacob Ziv. What do they have to do with this? Accept encoding. Whoa, awesome. Gzip, deflate, broadly. What is even broadly? There will be illustrations. Of what? What are these blocks even? Let's figure this out. We will be waiting. What will we be waiting for? In this season, hottest codebuster. Codebuster. Get it? Get it. Knock, knock. Who's there? File compression. Talk. Made some spelling mistakes along the way. Hey, my name is Irina. I'll be talking today about file compression. I write code from day to day with Scripto. They are a really cool, rad bunch of people. We help script writers be more productive in their day-to-day lives. And I write Node. That's kind of what I will be talking about here today. So compression. I kind of tricked you all into here saying that we'll be dealing with Phil Collins. In fact, we will be talking a little bit more about HTTP compression rather than actual file compression in general. So a little bit more focused, probably a little bit more useful for your day-to-day. So I kind of tend to do a bunch of research before I give a talk, and I was reading a bunch of papers about kind of compressing and minifying your files when you work, and seeing what it is that eventually you'll need in your day-to-day jobs. And like this one paper came up and said, okay, so roles of JavaScript are extending far beyond XML and HTML DOM manipulation, which I thought was kind of a cute thing to see in a paper, because I mean, obviously, because we don't just manipulate DOM these days anymore. And so in general, what comes off is that we are writing a ton of JavaScript, and there is a bunch of JavaScript traffic coming through on day-to-day basis. And so eventually it's just a lot of traffic that slows down our internet and things like that. So I wanted to see, and like one of the things that they were talking about is the fact that if we compress and minify our files, we can save up to 50% just by doing that. And so I was kind of wanted to think about more about the fact that we write our code and then we zlib it through gzip or deflate, and we kind of write this piece of code that turned out looking like this on a big screen to compress our files. But I wanted to kind of dive into it, exactly what's happening here and how we can use it on our day-to-day lives. So this one's using zlib. This is technically JavaScript that got mumbo-jumbled together. It got minified. So let's kind of look into this, and let's kind of dig into HTTP compression. Cool. So what happens with compression is that you have a file that you basically looks like a little doc.html in case of this index.html file. What you then end up doing is you end up zipping it through and trying to get a smaller size. What your end goal is just getting a smaller file. So you gzip it. And then once you look into it, you get a much smaller version of that file. And what happens in between is compression. So let's look into what exactly that is. So I said we'll be talking about HTTP compression. So that's kind of the interesting way to think about it, is that you are going to be sending files over from the server to the client based on the client's parameters. So you end up having a client that sends in a heading, and that's this accept encoding heading is what lets the server know in what compressed version of a file it will accept stuff in. So this client, for example, has got 3 different formats it can work with: deflate, gzip, and broadly. And the server will send over the stuff based on whichever kind of way it wants to handle that. Because it has 3 different ways it could handle it, it can choose one of the 3. So it could send it over in broadly, gzip, or deflate. And then if you were to kind of look into your usual developer tools and you wanted to see, okay, what it is that I'm working with, you can see that on your request, or on your request headers, you except encoding is just right there. And similar to response headers, you got the content encoding there. That's how it looks like. And this is what your client and server communicate with and when it comes to encoding. Cool. So we'll be talking about mostly these, except the CDCH, just because that's already getting deprecated. So in Chrome 59, so the latest version of Chrome, they've completely discontinued it, so that's kind of not a thing. So the major ones are gzip, deflate, and broadly. So we'll start with deflate because it's kind of like the most basic version and kind of how most of them came to be. So when you start with deflate, deflate's composed of two algorithms. One's Huffman and one's LZ77. Now I've been traditionally kind of not going into those, but when I do this talk, but I kind of wanted to explore them a little bit more because I think it makes more sense as to how these work, as to how compression works in general. So let's start with Huffman coding. What you end up having is you start off with a data stream. So a lot of these compression algorithms work with streams, which is amazing. So you start off with a data stream, it's got some data in it, you can kind of go through it. And what you do is you go look at that data stream and you generate a frequency table. And a frequency table just lets you know how many times a single block of code appears in that particular stream. So C appeared once, A appeared 3 times, and B appeared 4 times. And what you kind of sometimes a useful thing to do or not a useful thing to do is you get the probability or the frequency or like the probability of that letter occurring in the stream. So based on those numbers, we can see that it's 1/8, 3/8, and half, respectively. So what you then do is you do the Huffman trees. And the Huffman trees is kind of exactly how this kind of entire Huffman thing comes about. Everything's kind of about the trees. So let's build one up based on our data stream. So we know that C appeared once, A appeared 3 times, and B appeared 4 times. What you do is you go from your right-hand side and you build it up, and you make a tree and make connections based on those. So your first leaf would look like this, and what you do is you add the number of times that something appeared, which would be 4 in this case, the letter A and C, and you build that leaf up, and then you go right, keep going to the left from right, and you build up the tree like that, and again you add up the number of times something occurred, which would be 8, and that's your tree based on that little data stream that you have. So in that tree you have values, you have frequency that something appears, and you have the probability should you wish to have it. And the little leaves. That's why it's called a tree, because it's got leaves and trees. Some nice music going on next door. And then what you do is you go down and you create your encoding for this particular tree. So you start again from the right, and your rightmost branch is always 1, and then you go to a 0. And then you build up the entire tree again. So considering our right-hand side is the one that's much more, it's got more things going down, you will add a 0 because it's the left branch to the branch down. So it would be 1, 0, and then you start with a 1, and it's because it's a right-hand side branch, it's a 1, 1. And the end code would be the one that goes all the way at the bottom. So you can imagine like a much larger tree will have something else. This one's just 0, 1, 0, 1, 1. That's how you end up the last tree. So that's that was Huffman trees and Huffman coding, and that's part of deflate. And then I promised like Abraham Lempel and gzip, so they are the ones that came up with LZ77, and this one gets used and gets fixed up and gets reused in various different ways, and also kind of an interesting thing to explore. So for this one, again, you have a data stream that you work with. And you kind of divide your data stream into windows. So in our particular data stream, this will be like one window. And that one window is made up of 2 things. A search buffer. A search buffer is already encoded, so it's been coded through. And you have the look-ahead buffer. That's the one that you're going to be going through. And what you do is you kind of figure out where your search pointer is, and you say, okay, so the letter B is 4 spaces away from letter A, and that will be your distance, and that's part of your code that you end up at the end. And if you have various parts of your data that are similar, and it could be like 2 at a time, 3 at a time that are exactly the same as a different chunk in the search buffer, you add them up and you give it a length. So the entire thing is then made up of a length distance pieces. Um, so that's deflate. So deflate's made up of those two, and then everything kind of stems up from that. So deflate's kind of used in pretty much most of the compression algorithms that we know, like zip and gzip and pngs and things like that. So everything kind of stems off from that. So we have a tree of our own, basically. So let's look into what deflate actually is. So again, you have the data stream, and then you have 3 different bits that you work with. The first one is letting you know whether in this stream you'll have more data coming through or no. So 1 will indicate that it's the last piece of the data stream, and 0 will indicate there is none. And then you have raw data and the static Huffman blocks that we talked about earlier. And then you'll have dynamic Huffman blocks that are changing off. So then the entire algorithm is made up of pointers, and those are the ones that LZ77 provides, and the weighted symbols, and those are the ones that are Huffman trees, and that's your compression. So let's look at a gzip. Gzip is actually kind of like a different version of deflate, basically. And gzip is very well implemented in something called zlib. And zlib is something you might be familiar with already. It's part of the Node API, actually, if you write Node. And in general, zlib is probably one of the most popular libraries out there, aside from like MySQL or something like that, or SQLite. So super well known, super well used, and it's like your favorite compression algorithm that you work with. And zlib is really awesome because it allows you to have more control over your processing power and your memory use, and you can toggle all of these up to kind of have better trade-offs, so whether or not you want like a better compression or just a faster algorithm. So you have like 9 presets that you can work with to figure out what it is that you want, 9 being the most compressed and minified version, like the most compressed version, and 0 being like not compressed at all, so you end up using something like this. So in Node, like I said, there's required zlib that has that implemented for you. And so let's actually, let's work through it and kind of implement something of our own that we can use. And I have a chair for that. Amazing. Okay. Awesome. So I started off with, so we're going to do it on the server side, right? So we'll have somebody making a call to the client, and then client will be making a call to our server, and we'll be compressing stuff as we go. And we'll be doing it in Node because just easier that way, and that's what I do. Okay, so we'll need a server. So we'll just require HTTP. I think I should rather sit down. So we'll need an HTTP, and that's kind of small, isn't it? Is that better? Can you see in the back? Cool. So we'll have an HTTP, we'll have an FS, and then we'll need zlib to actually handle our compression. Awesome. So I've created a server. We're going to listen on 8080. Are we going to listen on 8080? In case I have conflicts. Yeah, we're going to listen on 8080. And we're going to work through compression. So like I previously said before, all of these are kind of getting passed on through our headers. So if we're looking at accept, encoding is the header we'll be looking for. So let's actually grab that from our response, or from our request. So we'll call it var accept. I forget things, so accept encoding, and if we don't have that, let's say that in case we didn't get that in, let's just make it an empty string. And so what we then want to do is see what kind of accept encoding we get, right? So what kind of parameter we get. So if we get, let's actually copy this over. Oh yeah, and I was going to use pump because pipe is sort of broken. So we're just gonna pump. So we're working with streams, right? So because everything. Whoa, hello IRC. Sorry about that. I'm just gonna close that off because. So we're using stream, so let's actually create a source that we'll need. So we'll create a read stream, read stream, and I have like an empty index.html file. By empty, I mean it looks like this, and it's just like a simple meow file. Doesn't matter. We just want to see like what the file size is and stuff like that. So deflate, zlib comes with the deflate parameter that you can work with. So if we get in our accept header, if we'll get deflate, we kind of want to zlib and deflate the file. If we have zlib, if we get gzip in our parameter, we want to be able to do the same thing. So gzip, and instead of create deflate, we're gonna create gzip. And else we'll just write an empty 200. And everything's good. So pump is just a better pipe, which is why I use that, and it takes an error handler as like the last thing, which is why it's good because it handles all the crap that could go wrong when you're streaming. So I'm just gonna write like a little handler that handles our errors for us in case that happens. Cool. So then awesome. So then what we want to actually see is whether or not, well, how long does one of these take? Because that's important, speed. And we want to see whether or not, which file size is smaller, and because that's what we want to know when we compress, right? Cool. I have standard running in case I make errors. Oh, and that's, yeah, I've declared that twice. Cool. So let's actually kind of start up a server and start looking through all of these. Okay. So we'll start up a server on index.js, and we'll just make a call to like localhost. Curl, let's do just a simple one for now to 8080 to make sure everything works. Cool, nothing happens. My pumping, oh, because I didn't actually pump at the very end. So we want source and a response and handler to get the regular file. So let's do it again and restart this server. And just make sure we get the initial file. It's good. Cool. So it gives us that, which is awesome. So just a regular file. But now let's actually handle the compression, right? So I'm gonna give it a -I so I get some stuff back as well. And let's give it a header that we need. And the header is gonna be accept encoding, because that's the one I said we need to pass through. And let's start with gzip and see what that is. Cool. So we compressed that file over. We got the gzip encoding back. Got that. So I want to see how long. Let's actually see what's the file size with this. So I'm gonna go back and I'll silence this, and I will just measure this by word count. So I'll pipe in a word count and see just the number of characters that the gzip file comes back with. That comes back with 2,109, right? So we need something to compare it to. Let's compare it to our deflate header. So deflate will look kind of the same as gzip. It doesn't matter what it looks like, but let's actually look at the word count, right? So deflate comes back with a little bit less than that. So they're pretty much relatively similar, right? But let's look at the time, right? We want to see the number, well, how long it's going to take us to get that. So I'll also silence this, and I'll just use time to see the time it takes. Cool. And so my touchpad doesn't work, but you can see the 0.18 over here. And this was with deflate. And let's compare it to gzip. Kind of similar. But then the interesting thing about this, okay, so these are pretty small, but let's get rid of all the encodings and time it otherwise. Curl, no URL specified. Oh, because I got rid of the header. Cool. 0.15. It's kind of timings. But let's look at another algorithm I wanted to show you, and this one's called Broadly. And yeah, and what Broadly is, it's kind of a newish algorithm that's come out. Google put it together, and now all 4 major browsers accept it. So then if we look at it, what happens is that it's specifically meant for HTTP compression. So it has a stream of blocks just as it does. It looks, when in deflate you got literals and the LZ77, in Broadly you kind of have commands instead. So it's easier to pass in the alphabet that the Huffman blocks provide just throughout your entire program. So then you're able to compress to a much smaller size. And it comes, what's super cool about it is it comes with a dictionary of commonly used HTML terms. So then if you have things like div, or you have things like head or section or article in your HTML, you're able to get a much smaller compression. But the thing is that it's like a lot slower. So I wanted to show you what that would look like. I'm not going to code it up, but I have like a preset example of what that would look like. So I'm going to use the lol in case I forget version of that. And then instead of gzip, I'll pass in Broadly and I'll time it. And that one takes like 3 times the time, 0.061 seconds. A lot smaller. But the thing is, if we look at it, and then instead of timing it, we just look at the word count. The word count is like half the size, if you remember, or like a little bit smaller, a lot smaller. So the previous one was 2100, this one's 1720. And again, it will depend on like what kind of file size you work with, but also a lot slower. So what I've seen a lot of the things I've looked at, a lot of people were using these for static assets. So the things that you don't have to do on the fly, and you can pre-compress and spit up like a worker on your, or just spin up another job, a cron job, to compress your files and then just serve them up as it comes, so you don't have to compress it, because decompression takes the same amount of time as gzip. So it is way slower. I kind of wanted also to mention something called Snappy, so I said this is really slow. And Snappy is another Google algorithm, but all it does is it's based on the LZ77, but it's like way faster than the original one does, but it doesn't compress very well. So if you need to kind of work between your RPCs and you need to send data between the two, you're able to do this. It still compresses to something a lot smaller, but then you're able to not waste as much time. I tried to give an example with Node Snappy, but I had a different Node version installed, so it didn't compile properly. And then I had to like recompile, and it would take like an hour to recompile. So I'm not going to give you an example, but you can look into this package. There's a Node implementation of that. If you needed something that's fast, but doesn't give you the same amount of time. So today I kind of talked about a bunch of HTTP compression algorithms, and I hope you've learned a bunch and hope you will be able to use this in your day-to-day jobs. I definitely use a bunch of gzip, so that's cool, and it's really awesome to be able to understand what exactly happens and be able to toggle that kind of information. Thank you so much for having me.